All right. Good morning, everyone. Today we'll wrap up chapter 3, op amps. There are a couple of circuits I'd like to go over. There's an example of an inverting amplifier, and then active filters using op amps. So at the beginning of the chapter, I mentioned about using an operational amplifier as a filter circuits that we learned in 201 or studied in 201 were passive filters. Passive filters mean they don't have any external power supply. They simply do filtering functions. But the op amp, introduction of an op amp creates an active filter where you can actively impart any gain to the incoming signal. So let's look at the first example. That was for the non-inverting, for the inverting amplifier. So the standard inverting amplifier has one resistor in the input path, which is right here, R1, and the second one providing feedback from the output back to the input. There are few drawbacks of the circuit. The first one is that the input impedance of the inverting amplifier is simply the resistance R1. Okay, so as an op amp by itself has infinite input impedance or very high input impedance. But when you create a circuit using an op amp, the input impedance changes depending on the design of your circuit. So for an inverting amplifier, it is simply R1. Secondly, if you wish to have a certain amount of gain, certain value for the gain is, of course, given by the ratio of R2 over R1. Right? The gain is R2 over R1 minus R2 over R1. Anyways, the ratio of R2 to R1. So in certain conditions, we are limited by the values of these resistances. For instance, if we wish to have the input resistance R1 as 10 kilo ohms and we wanted a gain of 20, then we'd have to, so example, R1 is 10K and R2 would be 20 times 10, so it would be 200K, which itself, again, creates a lot of other problems. So there are various circuit configurations that we can look at when it comes to designing an inverting amplifier. And this is one of those conditions. Okay. So here we have an op amp. And we can see that the positive or the non-inverting terminal is grounded. Input is going into the negative terminal. Hence, it is an inverting amplifier. It's an inverting amplifier. Input path has one resistor, R1, similar to the standard configuration. However, the feedback loop, the feedback path, has 3 resistors or multiple resistors instead of just one. So if you're presented with such a circuit, how do we analyze this? And that's what you're going to do. So the question would be, derive an expression for the gain of this op amp. AV, of course, is V out or V in. Or we could simply say, write an expression for V out. Okay. All right. So the first thing we do is we check whether negative feedback is present from the output back to the input. So yes, negative feedback is present. So negative feedback is present. So it can work as a amplifier. Secondly, is the differential input voltage and the current going into the op amp, are they equal to 0? Here we can say that yes, non-inverting input terminal is connected to ground. So if one terminal is connected to ground, we can state the other terminal also is at virtual ground. And if they are at virtual ground, then VI is equal to 0. And at the same time, we can say II is also equal to 0. Okay. So the input voltage, the differential input voltage into the op amp is 0, and the input current into the inverting terminal is also 0. Okay, so those conditions are satisfied. Now let's look at the rest of the circuit. Once you establish the op-amp conditions, and we establish that, okay, negative feedback is present, input voltage going to the op-amp is 0. After that, we simply apply our standard analysis techniques in any way we want. So Ohm's law, KVL, KCL, as required. Okay, as required. The circuit analysis techniques do not change. There are only 3 primary laws: Ohm's law, voltage law, and current laws, and those are the ones that we use to solve any circuit. Okay, so let's take a look. We have 3 resistors here, and the key thing to note here is that R3 is connected to ground. Okay, right here. Now, when I say ground, it's simply a common terminal. Okay, it could be a floating ground, meaning the circuit is not physically connected to a physical ground connection. Right? If you're running an op-amp circuit off of a battery, then there is no actual physical ground present in the circuit. So ground in that case would be like a floating ground that is simply just the negative end of that battery. Does that make sense? Right? So in this case, we see the bottom end of R3 is connected to that common terminal or ground, which basically are all of these. Okay, all of these are also connected there. So let me just draw out. And then from here, so all of these are connected together. Plus, yeah, I flip this, but I just want to draw it out differently in the sense that if R3 is connected to ground, then this point is connected to this point, which is basically your non-inverting terminal. Okay, so R3 is also connected to V plus, the non-inverting terminal. Let me change color here. Also connected to RL, the negative end of RL. So again, in 201, I was always fond of telling my students, always extract as much information as you can from the given problem. I'll state it again here. The information is not just in the problem statement, it is also in the circuit diagram. It is also in the system diagram, okay? So when you notice a circuit that has this ground notation, all of the points in the circuit that have that ground notation are all connected together. Okay, it's just an easy way for engineers to actually, or design engineers to actually make connections without making a big jumbled mess. So if we look at the input side, what do we notice? We have I1 that is flowing through R1, and then I2 that is flowing through R2. Our assumption is that the input current into the op-amp, II, is 0. So if we apply KCL, like KCL at the inverting terminal, we get I1 is equal to I2 plus II, and II is equal to 0. So we simply get I1 is equal to I2. Okay, all of the current that's coming here is going straight up. II is equal to 0. So I1 is equal to I2. And then if you apply KCL at that node, what do we get? Let's call this node as, let's see, you got 1, 2, 3, 4. So inverting terminal 1, non-inverting terminal, let's call it 4. I'll call this 2, and the output node as 3. Supply KCL at node 2. Node 2. Just like 2. Then I can write I2 plus I3. 2 currents entering and 1 current leaving. I2 plus I3 is equal to I4. Okay. Those are the initial things that I can see in the circuit. Okay. Now, I have my KCL. What can I do with it? I have I1 equals I2. Next logical step would be to apply Ohm's law and express I1 and or I2 in terms of the resistor voltages. Okay. And the way we would do that is we would again use the fact that II is equal to 0. So the voltage at 1 is equal to 0. I can write I1 is equal to VR1 over R1. And I can describe the resistor voltage R1, VR1, in terms of the node voltages at either end of that resistor. So it's V in minus V negative, meaning the inverting terminal, divided by R1. And since V negative is 0, it would simply be V in over R1. V in over R1. Makes sense so far? Any questions? Okay. All right. Then what can we say about I2? I2 is the same, but in terms of voltages, I can write that I2 is VR2 over R2. Right? VR2 over R2. And similarly, I can write I3 is VR3 over R3. Okay. So now if I want to write an expression for VR2 and VR3, let's look at that loop. What do we see? We have this loop right here. And I'm going to show you how we want to visualize this. Okay. So since we say that there is a virtual short between the inverting and non-inverting terminals of the op-amp, if you ground one terminal, meaning if you ground or you connect the non-inverting terminal V plus to 0, then V minus is also 0. Virtual ground concept. So I can draw the loop for R2 and R3 in this manner. That's R2. And this would be R3. And then both are technically connected to ground. This is the physical connection that is already shown to us. And this is the virtual ground. Okay, virtual ground. This is R2. This is R3. Let's bring this down. Okay. Again, the goal is to write VR2 and VR3. If you take a look at the current directions, currents entering from the left for R2. So voltage drop across R2 would be plus on the left, minus on the right. For R3, it's entering the bottom. And so plus below and minus above. Which makes sense because we are essentially saying that they are in parallel. Both ends of those resistors are connected to the other resistor. Okay, one end of R2 is connected to R3 on the right, and the other end is virtually connected to ground. Then we have I2 coming in this way. We have I3 going this way. Okay. So far, so good. The virtual ground. Yeah, so this is the virtual ground concept in the op-amp. Is because the op-amp impedance, op-amp has infinite input impedance. So an ideal op-amp does not allow any current to actually enter the op-amp. So if it's not entering the op-amp, then the volt, so basically the input current is 0. Also, if you ground one terminal, either the inverting or the non-inverting terminal connected directly to ground, that means that terminal has a potential of 0. Because there is no current flowing between the two, let me just go back to the circuit where I had input impedance. Okay, because there is no current flowing through those terminals, if you ground one terminal, we say the other terminal also has the same exact potential, meaning the voltage drop across the two terminals is equal to 0 because there is no current flowing through those terminals. And if the voltage is 0, means it's the same, we can extend the concept. I mean, there would be a physical ground at the non-inverting terminal, and we can say the inverting terminal has a virtual ground. So if this is connected to ground, it might be a physical connection, and the other end would be virtual ground. It is also at the same time, so that's the concept of virtual ground, meaning both terminals are shorted together. At the same time, if we wanted to analyze the circuit in a different manner, meaning if it suited our purposes, we could also state instead of being shorted together, they are infinitely open because there's infinite resistance between them. So if one terminal is not, one terminal is connected to ground or some sort of voltage, we can say instead of being virtual ground or virtually connected together, they're virtually open. But again, that's a different discussion. So it's kind of like conflicting conclusions at the same time. If it suits our purposes or our model, we can say it's virtually shorted. If it doesn't, we can say it's virtually open. For the purposes of our analysis for inverting amplifiers, we use the model where they are both virtually connected together, virtually shorted. And again, I would remind everyone that nonlinear elements, active elements like an op-amp, transistors, diodes, they have many different kinds of models, equivalent models. So you would try analysis with one kind of model, look at the solution, see if the solution makes sense within our system. If it doesn't, then that model is not valid for that circuit in those boundary conditions. We try a different model, and if it works, then we say, yes, okay, this model is valid. Same circuit, but depends on how you're looking at it. Okay, so going back to our loop, we have R2 and R3, VR2, VR3. We have the equations for I2 and I3. Now, I'm interested in I3 because I3 is the one that's actually going to the output, right? I3 and I2 combine to form I4, and then I4 is the one that is going to output V out. So let's write it in terms of I3. I3 is VR3 over R3. VR3 is the same as VR2. So VR2 over R3. And I can write VR2 in terms of Ohm's law. So R2 over R3. And one more step is I2 is the same as I1, right? So I1 times R2 over R3. I'm working backwards. When we analyze this kind of circuit, again, the goal is to find the gain. The gain A or AV, voltage gain, is given by V out over V in. V in is a known quantity. We want to predict what V out is going to be, right? So we are working backwards. We are starting at the far end, right here. We are working backwards to obtain V in into our equation. Okay. So again, just a recap. I started here. I know that I4 is going to VO. I4 is given by the sum of I2 and I3, right? I need a way where I can include V in into those equations. So what I did was I wrote a KCL at node 2, which gave me I2 plus I3 is I4. I wrote out the equations for I1, I2, I3 from Ohm's law, and then just plug everything into it until I obtain V in. So once I have I1 times R2 over R3, I1 is given by V in over R1. V in over R1. And so I'm going to plug that into the equation, and I can write I3 is V in over R1 times R2 over R3. Let's take a pause. What do you think over that? And let me know if you have any questions. Again, this is just one kind of circuit, but no matter what kind of feedback circuit you have in the, in the loop, the approach remains kind of similar. Different circuits, we'd have to use different analysis techniques. In real life, of course, design engineers who are working with these kind of circuits have to do multiple iterations of the same circuit until they arrive at an answer. So far, so good. Okay. All right, then let's see. Before we go to the output loop, let's look at this equation. I2 plus I3 equals I4. What can we do about that equation? So we have I2 and I3, right? I2, so I'm talking about this equation, and I2, I can plug in the values from above, and I3, we just found what I3 is. So we can plug both of those into this equation. Let me call this equation as equation 2. Let's label this as equation 1. And we can actually, let's call this equation 3. So we take equations 2 and 3, sorry, we take equations 1 and 3 and plug it into equation 2. Okay. So plug equations 1 and 3 into 2. So I can write I4 is equal to I2 plus I3, And I2, of course, is V in or R1. And I3 we just found as V in times R2 over R1 times R3. V in is common, we take it outside, and we can write an expression for I4 as V in times 1 over R1 plus R2 over R1 times R3. Right now, I want to leave it at that. We won't combine it yet. We can combine it in the next few steps if we need to. But I have an equation with V in voltage and the resistances. Okay, again, the goal is to find the voltage gain, meaning I want an equation of V out over V in. I have found an equation that uses V in and the resistor values. Now we need to do the same on the output side. Let's take a 10-second pause before I move to the output. Let me know if you have any questions. Any questions from anyone? Okay. All right, let's look at the output loop then. Now bring the circuit up. Output loop is right here. We have a resistance RL. This stands for load resistance. V out is taken across that load. That current I4 is coming down from the top. I4 is coming down from the top. It could go either way, depending on the circuit configuration. It could go into the op amp, as a reference direction. But let's draw out the output loop. One thing, the first thing that I notice, of course, is that this node is the same as node 4, right? So I can see that R3 is connected to node 4 by the virtual ground concept. Sorry, not virtual ground, physically connected to ground. And so RL and R3 kind of form a loop. So if I wished, I can draw a loop simply consisting of R3, R4, and RL. That is because R3 is connected physically to ground. So let's go ahead and do that. So if I was to draw that circuit, I would have.
I'm gonna have to watch my sheets now. I just.
Output loop. We have R4. We have RL. On this side, we have R3. I'm not including R2 because there is no need for it right now. All I need is these two. Okay, this is node 4. And this is node 3. And this would be node, wait, hold on. 3. And that one's 2. Yes. This is node 2. So this is R4, R3, and RL. And you're taking V out across RL. We have VR4, and we have current I4 flowing in this direction. And then R3, of course, has VR3 Current direction was already given to us. If not, we simply assume. Okay, we simply assume. Okay, so now we are ready. This is the output loop. Actually, take 5 seconds. Think about how we arrived at this loop. Does that make sense? Any questions? Okay. All right. So now I can apply KCL if I wanted to, but we already did that for the input path. We simply have I3, I4. Let's see. And then we have I2 coming in. We are not including that for now. So let's apply KVL, right? Let's apply KVL. It's a closed loop. We can apply KVL and we can directly obtain an equation for V out. So let's do I will get VR3 plus VR4 plus V out is equal to 0. There are 3 voltages in the loop, like KVL in any manner that you're familiar with, and you obtain an expression for V out. You can say V out or VO is equal to minus VR3 plus VR4. The plus and minus right now doesn't make any, it doesn't make a difference right now because, again, circuit analysis, we simply make assumptions of the voltage polarities and current directions. We perform our analysis. At the end of our analysis, if the answers have a negative sign, it simply means the voltage is the opposite polarity and the current is flowing in the opposite direction. So it doesn't make a difference on how we assume current direction. In this case, the current direction is already given to us, so we are just using those. Now, apply Ohm's law, and I can write VO is equal to I3 R3 plus I4 R4. Ohm's law. And now I have an equation for I3. I have an equation for I4. We are simply going to plug those values into this expression. So at this point, plug in I3 and I4. I3 and I4 would give us, this is going to be a long equation. Okay, so there's a minus sign outside first. Then I3 is given by V in times R2 divided by R1 times R3. And this whole thing is then multiplied by R3. Okay. This is going to be the big equation. I3 is V in times R2 over R1 plus R1 times R3. And then I4 is bigger. Was V in times 1 over R1 plus R2 over R1 times R3. And this whole thing is times R4. And that should be it. Let's move this closer. Okay, all I've done is plugged in the values for I3 and R4 in there. But look, that is the equation that has both V out and V in. And that is the goal. So no matter what kind of circuit we have, we want to obtain an equation that has both V out and V in. And that's what we have here. All we have to do now is rearrange the terms so that we obtain V out over V in. And that would give us the equation for the gain of the circuit. So let's bring V in outside. And I can write VO is equal to minus V in times R3 and R3 cancel out from the first term. So I have R2 over R1. And then here, a little bit more complicated. So I have R4 over R1 plus R2, wait, R4, R1. Yeah, R2 times R4, R1 times R3. And then I take V in on the other side. Again, V out or V in is equal to minus R2 plus R4 or R1, combining the first two terms, and then the second R2 times R4 or R1 times R3. Let's see if it's possible to reduce this further. No, we got R1 and R3. So that is the final expression for V out or V in. So let's take a 10-second pause, actually longer pause. You write it down. Let me know if you have any questions. Any questions at all? Okay, just a recap. We have an inverting amplifier. The standard practice, of course, the standard steps, of course, is first step is to see if the negative feedback is present. It's present, then we can assume that Vi is equal to 0 because the inverting term, the non-inverting terminal is connected to ground, which is node 4 at the bottom. And because that is connected to ground, we can say total voltage input and total current input, Vi and II is equal to 0 by the concept of virtual ground or virtual short. Once we have established those facts, then we can apply any circuit analysis technique, any circuit analysis law as we deem appropriate. The goal is to find the equation for the voltage gain in terms of the resistors, in terms of the components. And so we apply KCL, KVL, Ohm's law on the input side, and then we again apply KVL, KCL, Ohm's law on the output side. We obtain an expression in terms of V in, another expression in terms of V out. Combine those equations and you obtain an expression of V out over V in. That gives us the gain. A standard inverting amplifier with only one resistor in the feedback path is minus R2 or R1. here, because we have multiple resistors, R1, R2, R3, R4, all of them are involved in the calculating the gain. So for instance, if all of the resistors had the exact same value, doesn't matter what value it is, let's say 100 ohms or 10 ohms or 1000 ohms, what would be the result? So if R1 was equal to R2 equal to R3 equal to R4, and let's just say 1000 ohms, 1 kilo ohm, then our gain would be minus, what do you get? 1 plus 1 divided by 1 plus 1 times 1 divided by 1 times 1. 3. Gain of 3. So if you're designing a circuit, especially if it is an integrated circuit, it is easier to design the same component over and over again. Okay. It's easier to fabricate, manufacture the same component over and over again, especially if it is inside an integrated circuit. So if you have, or if you're a discrete circuit, all you have are 1 kilo ohm resistors, and you wish to obtain a gain of 3, a standard feedback path would just be 1K over 1K. You would only get a gain of 1, which again, if you want a gain of 3, then this is the kind of feedback path that you would use. Also, the case in point that I made earlier before I began this example was, if we wished a larger gain, like say 10 or 20, and we had a large input resistance, R1 is large, then R2, the feedback resistor, goes to like 20 times that input resistance. In this case, for this circuit, I'll show you the advantage. Let's say if R1 and R3 are equal and have a value of 1 kilo ohms, and R2 and R4 are equal, the value of 10 kilo ohms. Then our gain is minus 10 plus 10 divided by 1, and then 10 times 10 divided by 1, for a total gain of 120. And the reason, of course, I took R2 and R4 as the same is because R2 and R4 are multiplied here, divided by the product of R1 and R3. So if I want a high gain, I would ensure that R2 and R4 have high values compared to R1 and R3. So by using a reasonably sized resistor, which 10K I would say is reasonable, I can obtain a very large gain exceeding 100. Okay. Does that make sense to everyone? Right? If I wanted to do this with one resistor, it would be, let's see, 120,000 ohms divided by 1,000 ohms. Or perhaps if I'm using R1 as 10K, then it would be 1 mega ohm. So big difference. So just by changing the feedback path, we can change the gain of the circuit. All right, questions. Homework on op-amp. There's op-amp fundamentals, and then inverting and non-inverting amplifiers. I believe there is a there's a similar problem in the homework also. There is one problem in the homework that students in the past have had issues with, and so I have a slide based on that. So we did the non-inverting amplifier at the end of last class, and we derived an expression for the gain of a non-inverting amplifier. This is problem 13.21 in the homework. So I just want to give students the steps of how to analyze the circuit, and then we'll take a break. So here the circuit is a non-inverting summing amplifier. The input is being applied to the non-inverting terminal, V plus. V plus. And then inverting terminal, we have negative feedback. Output is being fed back into the inverting terminal. So negative feedback is present, and you have multiple inputs at the input terminal. So it is a summing amplifier. So the circuit is a non-inverting summing amplifier. Okay, non-inverting summing amplifier. So the way you would approach this is, well, we have voltage is V out, which is right here, upper voltage. I'm going to call this VR1. Let's assume VR2 is plus minus this way. So we get VR2. Voltage at the inverting terminal and the non-inverting terminal, let's say VI is measured between the inverting and non-inverting terminal. If I apply KCL at the input terminal, let's say, because V is like this, let's assume IA going in like this and IB going in through RB. And I can make the same assumptions. KCL at the input would be IA, and this would be II plus IB is equal to II. II will assume to be 0. Therefore, IA plus IB is equal to 0. So this is from KCL at the input terminal. Okay, IA plus IB is equal to 0. But let's see what happens here. If I want to write an expression for the IA and IB currents, I need the voltages across RA and RB, right? So from Ohm's law, I can write this is VRA or RA, and this is VRB or RB. So far, so good. Okay. Virtual short, virtual ground concept. One terminal connected to ground, the other terminal is also virtually connected to ground. In this case, the inverting terminal is not connected to ground. The inverting terminal is connected to R1. If it is connected to R1, then the voltage at this point, of course, this is the exact same node. So the voltage at the inverting terminal, V minus is equal to VR1. And if V minus is VR1, then V plus is also equal to VR1. Virtual short concept. Right? Same thing that we did for the inverting amplifier. If one end or one terminal is connected to ground, then the other terminal is also connected to ground because of the virtual short concept. We call that as virtual ground. In this case, there is a voltage at the inverting terminal, which is VR1, voltage across the resistor R1. And so we can say that V plus, let's put nodes. There's node 1, node 2, and let's call this node 3. So Both nodes are the exact same voltage. So V plus is also equal to VR1, and I can write VRA as equal to VA minus VR1, and I can write VRB as VB minus VR1. Remember, goal is to get V out over V in. V in this case is VA and VB, summing amplifier. And then if you look at VR1, it forms a voltage divider if this is R2 and this is R1. We have the output voltage being divided across R2 and R1. We use voltage division principle and obtain the values for VR1. So voltage division gives us VR1 is equal to V out times R1 or R1 plus R2. And that is what we want. We want V out in our expression. We take this and we plug all of those into the KCL expression we found earlier, which is right here, IA plus IB equals to 0. And then you plug it in and we derive an expression for V out over V in. That's how you would solve this problem. Okay. So let's take a break of about 5 minutes. It's 11:02. We'll meet back at 11:07. In the meantime, if anyone has questions, I'm here. Feel free to ask. It's 11:03, so maybe at 11:08.